Okay, welcome students to this session number 35 in the subject of industrial metallurgy. And with this session, we'll try to complete our discussion on the binary equilibrium diagrams covering type 1, type 2, and type 3 systems. So we are only left with discussion on the equilibrium cooling of various types of hypereutectic alloys for type 3 alloy systems, and we'll try to finish off that in this session. So we'll take three examples to cover the three categories of hypereutectic alloys that can be formed in lead tin alloy systems. So this we have already discussed with you. This we have already discussed. Again, for your reference, just I have presented the matter over here, and this also has been discussed with you. So today I will take one case from this category, one case from this category, one case from this category, and for each of these three cases we'll discuss the equilibrium cooling so that we can see what microstructural changes are taking place when we cool the particular alloy right from the molten state till down to the room temperature. So here you are seeing the first category of hypereutectic alloys, hypereutectic lead tin alloy with tin in this range, 61.9 to 97.5. We have taken an alloy of 74% tin. We have marked this composition over here, and now we have taken this alloy at a very high temperature corresponding to point L. When it is in the molten state, it contains only one phase in it, the liquid solution with 74% tin. Relative weight is 100%. We cool down this alloy under strict conditions of equilibrium. That means at very slow rates of cooling, no change is observed in the alloy till you have reached point M, which represents to the liquidus temperature of this alloy. So as you reach point M, because you have reached the liquidus temperature of the alloy, the solid phase begins to appear in this alloy. The first solid phase that appears in the alloy, its chemical composition can be obtained with the help of this tie line MT, and you are able to see that this first solid solution is beta solid solution because we are in the liquid plus beta region, and its chemical composition is given by point T as 98.5% tin. So because it has just begun to form, we usually take it as 0.01%. The other phase that is seen in the alloy system under these conditions is the liquid solution, which has a slightly different chemical composition from where it had started, and bulk of the phase is still the liquid phase. So I have marked 99.98% as the liquid phase. Then you will say that as the cooling solidification proceeds and temperature falls from a point M till point N. Now at point N, at a lower temperature, the amount of solid phase has increased from 0.01% to 25%. Importantly, these critical nuclei have grown and taken the shape of dendrites. Chemical composition of both the solid phase as well as of the liquid phase has changed, and so has their relative amount. As the cooling proceeds and we reach from point N to a temperature corresponding to point O, we are just on the verge of reaching the eutectic temperature. This is a very important temperature, but before we discuss, let's see the microstructure at this temperature. You can see that the amount of solid phase, which corresponding to point N was 25%, that has further increased now to 33.99%. But your mind it, if somebody asks you what is the maximum amount of pro-eutectic beta or primary beta that can be seen in an alloy of 74% tin, the answer is this only, because just after this, formation of pro-eutectic beta would stop. This entire liquid would transform to, see, this liquid is of eutectic composition. Moreover, this liquid is present just at the eutectic temperature. So just in a while, with fraction of a drop in the temperature, this entire liquid will change to eutectic mixture of alpha and beta. So whatsoever pro-eutectic or primary beta was to form, it gets formed till the eutectic temperature is reached. So if somebody asks you what is the maximum amount of primary or pro-eutectic beta present in this alloy, answer is about 34%. So when you cross this eutectic temperature and somebody asks you what is the microstructure of this alloy at a temperature fraction below the eutectic temperature, that is at point P, so you will say the microstructure is this: entire liquid had transformed to alpha lamellar and beta lamellar, that is eutectic alpha and eutectic beta, and this pro-eutectic beta which was there is available as it is. Right now, what is the change? What are the changes that are going to happen as the temperature drops beyond point P? You see now the role of these solvus lines come into picture. At the eutectic temperature, whensoever this alpha and beta gets formed, please remember this alpha and beta that have got formed are of the maximum solid solubility of the solute in them. So the alpha that has got formed because of the eutectic reaction is containing maximum 10 in it, 19.5%. And the beta that has got formed because of the eutectic reaction is again containing the maximum amount of solute lead in it, 2.5%. And as now the temperature drops beyond point P, with lowering of temperature, the chemical composition of the alpha and solid phase would be given by these solvus lines, and they are, this alpha line is continuously showing, the solvus line for alpha is continuously showing a drop in tin content from 19.5 to 7 at 0 degrees centigrade. Similarly, it is showing a drop in lead content from 2.5% to 1% from 183 to 0 degrees centigrade. So at point Q, if you still you are in the alpha plus beta region, there would be alpha and beta only, but alpha would have changed in chemical composition, beta would have changed in chemical composition, and just because of this change in chemical composition only, the relative amounts of alpha and beta would have changed. Try to understand that here alpha was of 19.5% in, but at W alpha is of about let us see here, alpha is about this 12% in. So where has this 7.5% tin gone? This 7.5% of tin has come out of alpha, took along with some lead also along with it, and now has formed another solid solution which is beta. Similarly, beta has pulled out some lead from it, and along that excess of lead some tin also comes out, and this second phase gets formed, that is alpha. So what is happening with drop in temperature? Alpha is precipitating beta out of it, and beta is precipitating alpha out of it. So somewhere over here you see that in the microstructure we have alpha of not 19.5 but of 12%. We have beta of not 2.5 lead but only of 1.5 lead, and also slightly their amounts have changed from 30 to reduced to 28, and this has increased from 69 to 71. Similarly, when from you go from Q to R, that is you reach the room temperature, now yes, alpha which was containing 12% here and 1.5% here would have even fallen down in terms of solubility of their solutes. So here you now see that alpha is only of 9% tin and beta is only of 1.3% lead, and this is the final microstructure. Okay, similarly, if you take another hypereutectic alloy of the second category, that is containing tin between 97 to 99%. For your reference, we have taken the example of a hypereutectic alloy which is containing about 98% tin in it. So we mark this composition and we draw a vertical line, take this alloy at a very high temperature corresponding to point L when it is in a complete molten state. What you can see is that here it has just got liquid solution in it. As it reaches its eutectic temperature, solid phase appears. As further drop in temperature takes place, these solid critical nuclei have taken the form of dendrites. Then at point O, you can see that it has reached its solidus temperature, and it's just on the verge of getting completely solidified. These are the last traces of the liquid that can be seen in the microstructure of the material. To know the chemical composition of this last liquid that is seen in the steel, in the alloy, you can make use of the styrene OW. Then just below point O, when you reach a temperature just below point O, complete solidification has occurred, and now you can see there is only one phase in the hypereutectic alloy, and that phase is beta, and that phase is having the same chemical composition as is of the alloy which you are considering 100% by weight. But then as you move beyond point P and you reach point Q, this alloy gets the beta phase present in the alloy gets completely saturated in lead, and now it says that I cannot accommodate this 1.5 percentage of lead in it, and I'll precipitate this lead out of myself to some an extent, and this will lead to the formation of alpha. But because this alpha is coming out in the formation, another solid solution is coming out in the presence of an already existing solid solution, this will always come at the grain boundaries. So now you see that again it has got two phases in it, because it has moved into the two phase region alpha plus beta. This alpha that has precipitated as the second phase comes on the grain boundaries. Again, as you move from Q to R, the amount of alpha increases, and also the chemical composition of alpha and beta changes. The final microstructure of this alloy is this. Let's consider the last category of hypereutectic alloys when they have got more than 99% of tin in it. For your reference, we are taking an alloy which has 99.5 percentage of tin in it. We mark this composition, draw a vertical line, take this alloy at a very high temperature when it's in the molten state. This is the composition. No change occurs till it has been cooled down to its liquidus temperature. Solid phase appears in the system. We cool it. Solid phase grows into the form of dendrites. We further cool it, it reaches its solidus temperature. Last traces of the liquid are seen. Just when its temperature drops below the liquid the solidus temperature, it's in a single phase region beta. So this is the final microstructure. Even when you come down from here till down to the room temperature, no metallurgical change happens in the system, and whatsoever microstructure was just below point O, the same is at point P, the same is at room temperature. So this is the final microstructure that you get for this alloy, and this brings us to the end of discussion on this type 1, type 2 and type 3 alloy systems. Next, now we'll start with a very interesting topic, that is iron carbon systems, where we'll draw a very important diagram called the iron cementite equilibrium diagram, and we'll try to study all the details going around steels, cast irons, etc. Students, I thoroughly enjoyed sharing this session with you. I hope whenever you'll watch this session, you will also enjoy it. Thank you so much. Thanks for your patience.